In this blackboard session, I would like to look at how much probability is contained within a covariance ellipse of a multivariate Gaussian. This is a problem that often is of some importance in sensor fusion. So, more precisely, I want to verify the following relationship: that the probability of x minus its expectation transpose covariance inverse x minus expectation, probability of this being less than some number g squared is given by a chi-square distribution, cumulative such. So I write it like this: chi-square Chi2 CDF of g squared n degrees of freedom. That is the result I want to establish. To get there, I'm going to start by defining some matrix L. A square matrix that I want it to be so that L transpose equals P. So this is basically some kind of square root of the covariance matrix. Then I'm going to define something, another variable y. By taking inverse x times x minus its expectation. And then this is actually going to be, this distribution is going to be a standard Gaussian around an identity matrix with the same dimension as x, of course. Why is that? Well, it's because the covariance of y is equal to, we see that its expectation has to be 0 because x has expectation mu, so the expectation of x minus mu, according to our linear transformation formula, has to be 0. So only its covariance remains, and we had the formula for that too, that I derived on the blackboard. At least for invertible cases such as this. So here again I use what will use a trick. I just insert what P is. And immediately you see that I can do some constellations. And I'm left with identity matrix. So then I've shown this result. And then I'm going to introduce a couple of more results that I'm not going to show right now. I call them for some lemmas. Because a lemma is a mathematical result that is something I use to establish a more advanced theorem. So first I have something from example 210 in the book, which I also did show here on the blackboard. That if x has a standard univariate Gaussian distribution with variance 1, then x squared has chi-square distribution with 1 degree of freedom. So that's one result I would like to use. And then I have another result, which is an exercise in the book. That is about the sum of chi-square distributed random variables. Very similar to what I did for the sum of exponential random variables on the blackboard. So now let's say that xi is distributed according to chi square with k degrees of freedom. And then I have several IIDs such xi's, m of them. And that sum should be distributed also chi square, but with k times n degrees of freedom. So I just multiply to get degrees of freedom. So I'm going to take that for granted. Okay, and then let me again look now at the quadratic form. What is that quadratic form? How do you relate it to y? Well, x minus b transpose inverse x minus b. That is actually the same as the norm of y squared. Because, well, if you look at now, split this p inverse up, you get 1 L inverse here times this, and there's similar, you get an L inverse transpose on this side that goes together with that, so both of those gives you y, so you're basically y transpose times y transpose times y, that is the norm square of y. Then, since y now is distributed according to this, I know that every single element of y has a standard univariate Gaussian distribution. Then when I'm going to sum up the square y's, so squaring is done here, sum is done here, and then the result follows. Then I have a formula for how much probability mass is contained within a given covariance ellipse.